A fault line does not negotiate. It moves when it wants, as much as it wants, and nothing built across it stays still. Engineers have spent careers learning to work around seismic faults, routing roads away, sinking tunnels under, finding any alternative. But sometimes there is no alternative. Sometimes the only path forward is directly over the break in the earth itself. What do you build when the ground beneath your bridge is actively trying to tear it apart? The challenge starts with geology. A fault is not simply a crack. It is the boundary between two tectonic plates, or sections of crust, that move independently. On one side, the ground may shift north, on the other, south. In a major seismic event, that movement can be sudden, violent, and measured not in millimeters but in meters. Most bridges are designed to survive shaking. Earthquakes send waves through the ground, and modern bridge engineering handles those waves reasonably well, with flexible bearings, reinforced piers, and careful attention to resonance. Fault rupture is a different problem entirely, not shaking. Displacement. The ground on one side of a bridge literally moves to a different position than the ground on the other side. A bridge designed only for shaking will shear apart. The deck splits, the columns crack, the whole structure drops. For most of the 20th century, the standard guidance from seismic engineers was blunt. Do not build across an active fault. Design around it. Reroute. The fault wins. Then came a project that could not reroute. In the early 2000s, Taiwan was expanding its high-speed rail network down the western corridor of the island. Taiwan sits on one of the most seismically active zones on the planet. The boundary between the Eurasian plate and the Philippine Sea Plate passes directly through the island's western lowlands. The Chelungpu fault was already notorious. In 1999, it had ruptured in the Chi earthquake, a magnitude 7.6 event that killed more than 2,000 people and shifted sections of ground by up to 8 meters. The high-speed rail line had to cross it. There was no path around. The corridor was too constrained by mountains on the east and coast on the west. The viaduct would go over the fault, or the railway would not be built. The engineering team faced a choice that had no clean answer. They could design a bridge that tried to be rigid enough to survive displacement, or they could design one that accommodated it. Rigidity fails fast. A rigid structure hit by meters of lateral movement does not flex, it breaks. The team chose accommodation. What they designed was, in essence, a bridge engineered to allow the ground beneath it to move and still keep the deck intact and the trains running. The concept sounds simple. The execution was anything but. The fundamental problem is load path. A bridge works by transferring weight from the deck to the girders, from the girders to the piers, from the piers to the foundations in the ground. When the ground shifts, that entire load path is disrupted. If one foundation moves east and the other stays put, the deck spanning between them will crack unless something absorbs the difference. On the Chelungpu crossing, the engineers designed a transition zone, a deliberate section of the viaduct built with extra tolerance for differential movement. The span crossing the fault itself was made longer than standard spans. Longer spans flex more before failing. The bearings, the mechanical joints between the deck and the piers, were designed with far greater range of motion than bearings on ordinary bridges. Where a standard bearing might accommodate a few centimeters of horizontal movement, these were built to handle much more. The piers in the fault zone were also designed differently. Below ground, the foundations were isolated from each other in ways that allowed independent vertical movement. Above ground, the columns were reinforced to a higher ductility standard, meaning they were designed not to stay rigid under force, but to bend without breaking. Ductility is a concept worth pausing on. In everyday language, ductile means something can be stretched or deformed. In structural engineering, a ductile column is one that yields, it bends, cracks slightly, absorbs energy, but does not shatter. A brittle column fails suddenly. A ductile column fails slowly, giving time and warning. The piers crossing the Chelungpu fault were among the most ductile highway structures ever built to that point. But the design team still had a problem they could not fully solve with materials alone. The retained concern was this: even with all the flexibility built into the structure, a major fault rupture of 3 or 4 meters would likely exceed what any bridge of that span could absorb without damage. The honest engineering answer was not that the bridge would survive intact. It was that the bridge would survive without catastrophic collapse. There is a significant difference between those two outcomes. Intact means trains keep running. Without catastrophic collapse means the structure stays up long enough to be assessed, closed, and repaired. The design target, formally, was life safety and repairability, not zero damage, survivability. That distinction forced a second conversation. How do you make a bridge that can be repaired quickly after a fault rupture? Because a high-speed rail line out of service for 2 years is its own kind of failure. The answer was modularity. The girder sections in the fault transition zone were designed to be replaceable. The bearings were designed to be accessible and swappable. The repair sequence was mapped out during design, not as an afterthought. This was construction planning that started from the assumption the bridge would be damaged. In April of 2011, a different kind of pressure arrived. Not seismic, but financial and political. The Taiwan high-speed rail system had already struggled with cost overruns and ridership shortfalls since opening in 2007. The fault crossing segment had cost more than any equivalent length of the line. Questions were raised about whether the expense had been worth it. The engineers who had designed the fault crossing had no earthquake to point to yet. The fault had not ruptured since the viaduct was built. The design had never been tested at full scale. That is the uncomfortable reality of seismic engineering on long timescales. You build the safest structure you know how to build, and then you wait. The fault moves on its own schedule. What the engineers could point to was the 1999 earthquake record. They could show that the Chelungpu fault had moved by several meters in living memory. They could show that had a conventional bridge existed over that fault in '99, it would not have survived. And they could show that their design, by the best analysis available, would have. That argument is ultimately what justifies the cost, not certainty, probability, and reduced consequence when the worst happens. Other fault-crossing projects followed similar logic, though in different forms. In California, highway overpasses crossing the Hayward Fault near the San Francisco Bay Area were rebuilt after the 1989 Loma Prieta earthquake, using some of the same design principles: ductile columns, flexible bearings, designed in repairability. The Coronado Bay Bridge in San Diego was seismically upgraded specifically to handle the Rose Canyon Fault that runs beneath the bay. The upgrades were not cheap, and they were not visible from the deck. They were inside the columns, beneath the waterline, invisible to anyone driving across. That is the nature of seismic engineering. Most of the work is in what you cannot see. The broader lesson from fault-crossing projects is one that engineers in earthquake zones have absorbed slowly over decades. The goal is not to build structures that pretend faults do not exist. The goal is to build structures that know exactly where the fault is, what it can do, and what kind of damage is acceptable to absorb. Acceptable damage is not a phrase that sounds reassuring, but in engineering it is a specific and honest concept. A structure that can suffer controlled damage and still stand is more useful than one that either survives perfectly or collapses completely. The bridges built over active faults are not expressions of overconfidence. They are expressions of a precise and uncomfortable calculation: the cost of building here versus the cost of not building here versus the price of the worst possible outcome. The fault will move again. The engineers know this. The bridges are built for that day. Whether it arrives in 10 years or 100, the structure over the break in the earth will be waiting. The story of that day is still unwritten.